And action. Okay, what I want to talk about now is kind of to show you the mathematics of the equations that you need to know for this diffraction stuff. Now, this picture right here basically shows what this picture here is showing this at the top. We've already been talking about that. You have two sources that are creating waves. This is looking at them from the top. And where they meet constructively, you can get a bright spot and you can get series of bands of lines. And usually the ones we saw that we were just doing in the simulation, you hardly saw any bands at all. And it all really depends on the distance between the slits. It depends on the wavelength. It depends on how far away the barrier is. I mean, there's lots of factors that are going to affect the slit distance. But I wanted to talk about what exactly is happening here. Okay? If you notice here in the middle, and so it kind of helps to draw the waves like this. This is my spacing between the slits. And basically, a lot of the experiments will have the light source back here going through one slit, so it diffracts. And then it goes through two slits, like that. And then the last example, I think we got better pictures when we had basically two light sources. But this would basically act like those two light sources would. All right? And so what you get right here is that the light waves are traveling a certain distance here, and they're traveling the same distance here. What this picture is to illustrates is that the crest lines up with the crest, doesn't it? And when that happens, you get what? Constructive interference. And if you get constructive interference, you get bright light. Okay? Now, if you notice here, if this wave traveling here goes this distance, and this wave goes just a half a wavelength shorter of a distance, then what's going to happen?
Destructive interference.
Right, you're going to get this one here. You see this one right here makes a crest, and this wave right here hitting it makes a trough. And if the crest and the trough line up, then you're going to get destructive interference, and you're going to get a dark spot, aren't you? Now, you're going to get all kinds of things in between, which will lead to different brightnesses of the light. But where you're getting maximum constructive interference is in the middle, and where they line up and they cancel each other out, that's where you get destructive interference. And so this, remember when you walked along, you heard like a really loud spot, which would be like light, and then you heard like a softer spot, and I mean, you said you'd almost cut it out, right? And this is actually, they use this with noise-canceling headphones, don't they? Yeah. What noise-canceling headphones is they basically, I'm not exactly sure how they work, but I just know they use destructive interference. They basically take that incoming wave, and if they can get another wave that's half a wavelength out of phase. And when I mean half a wavelength out of phase, if you have a crest, and then half a wavelength would be a trough, right? If you can get that signal and create a wave that's half a wavelength out of phase to match up with that signal, they're going to cancel each other out. So, these places right here, on the line here, if I were to draw this right here, let me use a pen that works.
It's already drawn on there.
I know, but I'm going to move this paper in a second.
Oh.
Okay? This right here is your bright spot. So I'll call this, draw a circle here. I probably shouldn't use black light for my bright spot. Let's use a red pen for my bright spot.
A red pen.
And we'll call this my bright spot, BS. And this is the fringe. This is called, the fringe number is signified by m equals 0. So this is m equals 0. This fringe is a bright spot. This is m equals 1. And bright spot here, this is also m equals 1. So it's measured on either side. Now this used to confuse me a little bit. This spot right here is where they get complete cancellation. That's my dark spot. But for this fringe, that's known as m equals 0. And this dark spot is also known as m equals 0 for my dark spot. And then the next dark spot up here, which is not shown on this diagram, would be m equals 1 for my dark spot. And again, I get another dark spot down here. That would also be m equals 1. Make sense? All right, now, so what I'm going to do is let me get rid of this, and I'm going to draw my screen back here. And this distance between my screen slits is d. Alright, and I want you to pay attention to the first bright spot. If I draw a wave, I'm not going to draw the waves going like this. But if you notice right there, this distance obviously is greater than this distance, isn't it? Okay. Now what we can do is we can set up a triangle right here. And if we put a right angle right there in that triangle, and I measure this angle called theta. Well, we know that sine of theta is opposite over hypotenuse, isn't it? So opposite of that is d times the sine of theta, isn't it? Agreed? So this side is my opposite side, and that's d times the sine of theta. All right. How much farther is this than, how much farther is this line than this line that we say?
The distance of the opposite.
Okay, we said how many extra wavelengths was it? No, because we're going to the bright spot. So we want, it's going to be one wavelength farther, isn't it? What about here? Half a wavelength. So what they do here is I say, okay, if I want to get to this spot right here, then this distance has to be lambda distance farther, doesn't it? But I want it to be one wavelength farther. So I'm going to say this has to be m lambda, because m is 1, isn't it? Now if I want to get to the second bright spot, which is way up here on the graph, then this distance, now this has to go a greater distance as well, doesn't it?
Yeah.
But whatever, this distance, it would make a new triangle, but this distance would have to be twice, it would have to be 2 lambda greater to get the next bright spot, wouldn't it? Okay? Now remember that idea for m lambda. So I can say m lambda, first of all I can say m lambda equals d sine of theta. Now on your AP test, I want you to notice something on your green sheet for waves and optics. And the first thing you'll see here is on your green sheet, there's the equation. You know, there's focal length, it's half the radius of curvature. We've been going over that stuff. M lambda equals d sine of theta. There's the equation right there. So that's what they're talking about when they're talking about that equation. And they give that to you. But I want to talk about this next equation right there and how cool that is. Actually, it's not that cool. You actually don't really need it. Now, the other thing I want to show you is this. If I go from here to here, on the AP test, they call this distance from the screen to the slits, they call this L for the length. And it makes a triangle that goes from here to here, doesn't it? Now, this triangle is a similar triangle to this triangle. Right? Ask your mom to prove it. But these are similar triangles. And this angle is theta, just like that angle is theta. So this is the same as that. So what you can do, one of the things they love to ask you on the AP test is they love to ask you, okay, how far, I mean they'll ask you, at what distance is it from here to here? What's that distance right there, from there to there? Now on the practice test you took 2009, one of your questions says, what's the distance from one dark spot to the next dark spot? Well, wouldn't that distance from this dark spot to the next dark spot be the same as the distance from here to here?
Yeah.
Because this is a half wavelength shifted up, and that's half wavelength up. So if I go down a half wavelength, it's that distance there, isn't it? So all you had to do was find that distance. So to find that distance, all you needed to do was find theta. And if you knew theta, then you knew the length to the screen, and you could use trig to find that. Make sense? We may have to go through that problem. What time are we at?
9.
9? Okay, let's
About
stop
to be
it.
10.
Let's stop it, and now.